Okay, so today we want to talk about something called Riesz representation theorem. I've given the title. And the spelling is this. Okay. It's a spelling. We want to. I mean, there are several generalization of this, but we will be proving the basic theorem, and that's all. We'll stop with that. Okay. So the theorem we want to prove is the following. So before proving the theorem, so we will consider this. X is a compact metric space. We will prove this for compact metric space. We can generalize this theorem to general compact Hausdorff space or even locally compact space. And also, this is for a positive linear functional, we will state it. We can state it for a general linear functional also, but that needs a bit more work. We don't have that much time in this course. So maybe if it is needed later, we'll we'll prove the extension also. So we assume X is a compact metric space. Then we can talk about C of X. Okay, this is a separable Banach space. Incidentally, we didn't prove the separability for C of X. This can be proved using Stone-Weierstrass theorem. For instance, if you say take 0, 1, for example, or any interval, then we know that polynomials are dense there, and you can take polynomials with a rational coefficient, and that forms a dense subspace there. Once again, I'll just. So you can take polynomials with rational coefficients, and they will form a dense. They will be dense there by Weierstrass theorem. Or you can carefully use Stone-Weierstrass theorem by taking, rational numbers and other thing. Using something you can actually prove that. Maybe you'll see later that this is separable. Okay. Then then we can consider linear functional from C of X. This is the definition I want to make. Is linear functional from C of X to C. Okay. Is positive if f greater than or equal to 0 implies if you have a positive function, then this number has to be greater than 0. This is a number, complex number, and that has to be greater than 0. Okay. So this is what is called a positive linear functional. An example of a positive linear functional, you can take any measure, mu be any finite measure. X, a nice finite measure on X. Then f in C of X going to integral f dv. Okay. Then this is it's something, a number in C. This is linear, of course. It's clearly linear. It's a linear function. Is an example of is a positive linear function. That is just clear. If you take any positive function, then the integral is also positive. Okay. Okay. So the Riesz representation theorem says that every positive linear function on C of X will look like this. Is given by a measure like this. In fact, it says something more. Every complex linear functional is given by a complex measure. Okay. For that, we need to do something, but we will prove it for a positive linear function. So that is what we want to prove. Before proving that, we want to prove a lemma. Okay. This is something about positive linear functionals on C of X. So C of X is an algebra. Most of you might have learned Stone-Weierstrass theorem already. And there you must have encountered that C of X is an algebra, facts like that. C of X is actually, it's a vector space and it's also a ring. So whatever I'm going to state, it actually true for more than a C star algebra. More than a C of X, it's true for a general C star algebra. And we'll prove it for C of X. The same proof works for any C star algebra. You can actually generalize it. Okay. So let X be a compact metric space as before. Okay, so we will fix throughout this class, we will fix X as a compact metric space, and C of X is continuous functions on that. Then we want to prove the following: a phi from C of X to C, a linear functional. Okay, or I should put outside it, or I could have said phi is in C of X star. Then the following statements are equivalent. Then the two statements are equivalent. Okay, one. So it is just a linear functional. Okay, I haven't even assumed continuity for that till now. So phi is positive in the above sense. F greater than 0. If I have a function greater than 0, then phi of F is also greater than or equal to 0. Okay. Then second one is it's automatically bounded. The function is automatically bounded. If it is positive, it's automatically bounded. Okay. Phi is bounded. It's automatically continuous, bounded. And the positivity condition is for a bounded linear function, the positivity is equivalent to saying norm of phi equal to phi at 1. Okay. 1, there is a function 1, constant function 1. Okay. So this is 1 is the constant function 1, the function taking value 1 for all x. So the norm of phi is equal to that. Okay. This is the lemma. So the positivity is equivalent to saying it is bounded and the norm is equal to phi of 1. Okay. Proof. So 1.
To show the definition of positive function at once.
Definition of positive function is just this. You take a positive function f, then phi of f is also positive. That's all. It takes positive function to positive numbers. Right?
Yeah.
Yeah, that's all. Okay. And example is the integral. So we are going to prove that everything looks like that integral. That's all. Okay. You came late? Oh. Okay. So 1 implies 2. Okay. So phi is a positive functional. Then we want to prove that phi is automatically bounded and phi is equal to 1. Okay. Assume phi in C of X star. No, it's not star. Sorry. It's not bounded yet. I mean, we haven't assumed it's bounded. Phi is a linear, just a linear function. Okay. Okay. So then we want to prove so we assume positivity and we want to prove it's bounded and it attains the norm. I mean, its norm is equal to phi of 1. We want to prove 2. Okay, so for that we do the following. We will define for fg in C of X. We will define an inner product between them. Fg equal to, usually when you have, so how will you define an inner product on C of X usually, or even L2? I mean, if you take, you can define the L2 inner product by integral over some integral with respect to some measure. Then you will get the completion will be L2. C of X will not be complete. So if you take the completion, that will be L2. Instead, I don't have an integral, but I use this linear functional phi to define an inner product like this. Okay, phi g. So this is not an inner product. This is a semi-inner product. This is clearly linear in the first variable. Okay. This is clearly linear in F, conjugate linear in G, and it's positive. That is, if you take F and F, which is P of F bar, which is P of mod F square. Mod F square is a function. Okay, and that is because phi is positive, this is greater than or equal to 0. Since phi is positive. Okay, phi is a positive linear functional, so it takes P of mod F square greater than or equal to 0. So because of that, we have the positivity condition is satisfied. It's linear, anti-linear. So this is a semi-inner product. And we have remarked when we proved Cauchy-Schwarz inequality, we have remarked that any semi-inner product satisfies Cauchy-Schwarz inequality. I mean, to get the other way, that is, suppose inner product of G equal to norm of G, then for that you need inner product. But for the inequality, you need only semi-inner product. Okay? And the positivity is of course needed. It's not a sesquilinear form will not satisfy. You need the semi-inner product condition. So this implies that it's a semi-inner product. So Cauchy-Schwarz inequality, we have inner product Fg, which is equal to phi of Fg bar, okay, that is less than or equal to phi of, so I take the square here, maybe. Okay. I mean, the mod is outside. So the square is outside, which is equal to mod f square, right? Phi of mod g square, right? This is the Cauchy-Schwarz inequality. Okay. Okay. Cauchy-Schwarz applied to this inner product. So now take G equal to 1. I mean, I want to prove, so this, I mean, my aim is to prove that norm phi is equal to phi of 1. First, I want to prove that it's bounded and norm phi is equal to 1. So I want to get this inequality, right? I want to get this inequality, phi of f. Phi of f, mod of this is less than or equal to the usual. Instead of norm phi, I have to get that phi of 1 and I should get norm of f. That's what I want to get. So I take G equal to 1. So in this, G equal to 1, oh, sorry. G equals 1 and f is f. So that will imply this is, so if I take G equal to 1, it becomes phi of f square, right? That is less than or equal to phi of mod f square times phi of just 1. Okay. G is 1, 1 square is 1, so phi of 1. Okay. But then we have this mod f square as a function is less than or equal to norm f, the infinity norm, times 1 square. That's the square, right? It's always to as function, okay, as function. That is norm f infinity 1 minus norm f square is greater than or equal to 0. This implies phi of norm f infinity times 1 minus mod f square is also greater than or equal to 1 since phi is positive. So this implies that phi of mod f square.
Sir, you meant norm f infinity square 1 minus norm mod f square?
Say it again. Okay. I got scared.
In the second line, that should be norm f infinity squared, right?
Norm f infinity squared. Here.
No, the below line.
Below line, yeah. Everywhere it's infinity square. Everywhere it's infinity square. Yeah, you are right. Okay, this is norm f infinity square. Because I don't see anybody. Suddenly some sound came and got scared. Okay, so this is norm f infinity square times phi of 1, right? This is just a number. So this times phi of 1. Correct? Right? So I have written it correctly. So mod f square is less than this. Okay. Now I want to bring this here. This implies. So what do we have? Oh no, sorry, not here. I want to bring this. Okay. This implies mod phi of f square is less than or equal to norm f infinity square. Phi of 1 is that there are two phi of 1. Okay. Phi of 1. Yeah, phi of 1 square. Phi of 1 is number positive. Okay. I mean, one is a function which is greater than or equal to 0. Phi of 1 is also positive, so there is no problem. That's fine. Okay. So this is just, I mean, you take that is phi of f is less than or equal to phi of 1 times norm. This implies, what does this imply? Norm of phi is less than or equal to phi of 1. Okay. So this clearly, this implies phi is, this implies phi is bounded. and we know that norm phi is less than or equal. I mean, we are first proof. I mean, now only we are proving that phi is bounded and phi norm phi is less than or equal to phi of 1. Okay, and further, phi of 1. If we just take phi of 1, you take the model of this. That is certainly less than or equal to norm phi times norm of 1 infinity. But norm of 1 infinity is just 1. So this is equal to norm. So we proved the other inequality also. So this implies norm phi equal to phi of 1. So we have proved. Fine. So we haven't done anything. We defined. So what we did is we defined a semi-inner product and we applied Cauchy-Schwarz inequality and we got this. Okay. Now we want to prove the other way. 2 implies 1. Maybe did I write the other 2? Okay. So that should be much easier. Oh, it's not. So we are assuming that norm phi equal to phi of 1. Okay. So we can divide by, I mean, norm phi assume. So we are assuming norm phi equal to phi of 1. And we can divide it by some number, and without loss of generality, we assume that this is equal to 1 without loss of generality. Okay. Okay. So what we need to prove? We want to prove that it's positive. Okay. Suppose f is greater than or equal to 0, or we assume that f is between f is greater than or equal to 0, less than or equal to 1. Okay. Then we want to prove phi of f is less than or equal to 1. Okay, that's true because its norm is less than or norm is equal to 1 and it's greater than 0. Okay, that's what we want to prove. Okay, that is phi of f is in, it's a complex number, it's supposed to be in this. That's what we want to prove. Suppose not. We want to get a contradiction. Okay, suppose not. Let phi of f equal to some complex number z, which is not in 0, 1. Okay. So this is something I tried some time back. I couldn't actually, I mean, it's intuitively clear what I'm going to say, but I didn't really immediately write a proof of this, but I'm sure it's easy. You can try this. Point is, I mean, it's in the book also. I'm just following the proof given in Sundar's book. Okay. There are different proofs, but this is a proof by Varadara. This is not the original proof. Okay. I'm going to give a proof which is given by Varadarajan or somebody, which is rewritten by Sundar later as a paper, and then it's in this book. Okay. So what do you want to say? Now choose z naught in a complex number and r greater than 0, some radius, so that such that the ball z naught with r contains this 0, 1, but z is not in b of z naught r. That is, you have the complex number and you have this interval here, and the z may lie somewhere. Okay, then you can find some ball like this, which is intuitively clear. I mean, or if you, even wherever it is, you should be able to draw a ball which does not contain the z but contains this interval, which is intuitively clear. But I tried to, I mean, just 15 minutes back, I tried to do that. I was not able to get. I'm sure you will be able to get it. Okay, this is the exercise. Okay, I'm sure it's very easy. Okay, so we can, I assume that we can get such a ball. Okay. So f of z, okay. So we assume that phi of f equal to z, a number, and z is not in the, phi of f is not in this open ball. Okay. So then what happens? Then now, so this, we assumed that f is, I mean, since let some x is in x, okay, since f is less than or equal to 1, greater than or equal to 0, okay, f of x has to be, I mean, f is a positive function, okay, and it's less than or equal to 1, f of x has to be in 0, 1. Okay. So this is in 0, 1, so f of x minus z0. Okay. And we know that this interval 0, 1 is contained in that ball. So this is less than or equal to r, less than r. Okay. It is contained in that r. It contains that open ball. It's contained in that open ball. So this is less than or equal to r. Okay. This is for all x in x. Okay. So this implies that this, if you take the infinity norm, that's also, so mod of f of f minus z0 times 1. I mean, z0 is a number, so 1 is the constant function. Okay, that is less than or equal to 1. This infinity norm, that is less than or equal to 1, right? Okay, that's fine. Okay, now consider this z minus z0. I mean, this is because this f is less than or, I mean, f is as a function, it is we have assumed that it's greater than 0, less than 1. So for any x, f of x should be in this interval 0, 1. Okay, and so that means since 0, 1 we have assumed that is contained in that ball, that satisfies this inequality, and from that, since that is true for all x, supremum over x is also smaller than that r, so we got this. Okay. Now z minus z0 equal to, by definition, this z minus z0 is nothing but phi of f. Okay, and we know that z0 is just a number. So f of, sorry, not f, phi of z0 times 1. Okay, I mean, z0 is a number, so you can take z0 out. Phi of 1 is 1. We have assumed phi of 1 is 1 initially. Okay, so this is equal to this. Okay, now this is less than or equal to, so this is, of course, you can, by linearity, this is equal to norm of f minus z0 times 1. Okay, that is less than or equal to norm phi, which is phi of 1, of course, times norm of f minus z0 times 1 infinity. So that is 1. So this is f minus z0, which is less than r. But this is, we have assumed this to be greater than, sorry, this is greater than r. Okay, because we have assumed that z minus z0, z is not in that open ball. Okay, we have assumed here. Because of that, this is greater than r and this is less than r, which is a contradiction. Okay. So it's okay. It's fine. Is this fine?
Yes.
Okay. So let us state the theorem. So to prove the theorem, I will require the following fact, which Anupam is going to prove. Okay. So that this is maybe another lemma or something. It is not a lemma, possibly a theorem, but for us, it's a lemma. Okay. So the lemma is the following. Every compact metric space is a continuous image of, is image of Cantor set. It's a subjective image of Cantor set. Okay. That is, there exists a P from Cantor set. So let's call Cantor set as, so the Cantor set, I mean, the Cantor set, there are different ways of writing it. For us, we can see what is, okay, from, let me just write Cantor set here. Okay, subjective, this is on to. Okay, so this will be proved by Anupam, and the proof is also easy. It's in the book. It's there. I don't know what proof he is going to prove. He says he will use Hilbert cube and all. So I don't know whether that is needed. But anyway, let's see that later. Okay. So what is Cantor set? The Cantor set is, see, you have the interval 0, 1, and you are going to take out this middle part and you are go on doing this. By this, what you are going to do is, if you have any x in 0, 1, then you can write this x as some point x1, x2, x3. This is not decimal, but this is in the base 3. I mean, triadic, no? It's called triadic, I believe. Triadic expansion, you can write it like this, where xi is something in 0, 1, 2. The Cantor set is something where the 1 doesn't occur. Okay? If x is in Cantor set, then xi is equal to 0 or 2. Right? The middle one doesn't occur. So you have an expansion, you have a triadic expansion, not decimal expansion, not base 10, base 3 expansion of any number in 0, 1. And that expansion contains only 0 or 2. That is what Cantor set is. Or you can write that as something like summation xi by 3 power n, right? N equal to 0 to infinity, 1 to infinity, whatever. Okay, xi is in 0 or 2. Okay. So Cantor set is nothing but as a homeomorphic. I mean, it's a homeomorphism. Homeomorphic to 0 to the direct product power n. 0 to cross 0 to cross, you take the countable direct product of 0 and 2. That is any two element set. So we assume that Cantor set, we denote Cantor set by 2n. Okay? It's just two element set, and you are just taking the direct product of, I mean, it's a finite set, you are taking the infinite direct product of two elements. That is the Cantor set. Okay? This is okay? Okay, so now I want to use this lemma. The every compact metric space is continuous image of that I want to use. Then I want to go through the proof of that. Okay, now proof of Riesz representation theorem. So first I will assume it's a Cantor set. Then I will assume a general compact metric space and use the fact that there is a surjection between Cantor set and Cantor set to this compact metric space, and use that surjection to define the measure we want. Okay. Okay. So first, assume x equal to Cantor set. Okay. So what do you want to do? Now we have a phi from C of x to C. Okay. Phi is positive, and we want to get a measure from this. Okay. Okay. So how do we do that? So consider this projection. We want to define a measure on this. So for any measurable set on the Borel sigma algebra, we want to say, so we want to define a measure on the Borel sigma algebra of x. That's what we want to do. So we consider this pi n from x is 2 power n to take, I mean, 0 to 1 and whatever. We can take 0, I will call it as 0 to power n, which I call it as 2 power n. N is just a number, finite number. Okay. So you call this as, I mean, which I am calling this 0, 2 power n. So pi n is the projection, which is just the projection. So any element will be like this, x1, x2, the infinite thing like that. That will go to pi n of this equal to x1, x2, up to xn. You take the first n coordinate, project it onto the first n coordinate. So this is this. Okay. Then you define an equal to pi n inverse of any set A, where A is contained in 2 power. It's a finite set. Okay. I mean, how is the top? So I hope all of you done some topology course and product topology. I hope all of you know. So the topology in the Cantor set is generated by this kind of elements. Okay. I mean, if you have any infinite product, x1, x2, plus xn, any possibly uncountable also, then the topology is given by you take ui1 cross ui2, where you take finitely many of them and then take the tensor product of x and the corresponding x remaining places is a whole set. In finite places, you take open set, the finite direct product of open set, and then you take the whole set. So that gives a basis, that gives a base for the topology, for the product topology. Base means you take those sets and you take finite intersection and take arbitrary union. That will give the topology. That will give all open sets. Okay. So the topology in Cantor set, which is the product of topology, is actually given by this kind of sets. By an inverse A. Okay. So now you take A equal to, this is a increasing union, A equal to union n union A, right? Okay. Okay. I mean, for a pi in inverse A, that the topology is given by in this topology. I mean, when you have the finite projection there, the topology is given by that. So any set in this form, pi n inverse A, is both open and closed. It's a finite set, of course. I mean, it's a finite set in 2 power n in this. So it's both open and closed. Okay. Right? In particular, the indicator function or the characteristic function 1a, A in A, is continuous. If you have a set which is both open and closed, then the indicator function is continuous. Okay. This is a connected component of that. Okay. I mean, whatever it is. So it is continuous. So a set which is both open and closed, it's continuous. It's fine. So now do you define, because it's continuous, we have a phi from C of x, I mean C of 2 power n to C. Okay. And you define mu of A for A in this A, script A, okay, equal to phi of 1A. Because, I mean, 1A is continuous and you can define phi on that, and phi of 1A equal to mu A. And notice that this A is an algebra. It's clear that if you have A, then A complement will also be in this 2 power n, and it will also look like that. And it's an increasing union. If you have two sets, then you can go to a bigger set and take the union. Okay. So it is an algebra. Okay. So you have defined a measure on this algebra, and mu is finitely additive since phi is linear. If you take mu of some disjoint set, then that will be summation of 1 AI, okay, or I mean mu of some disjoint set AI equal to phi of summation 1 AI, okay, and the summation you can take it out, okay, and then it will become summation of mu of AI. So because of that, it's finitely additive. Okay. Now notice that, yeah. Now since this is compact, and any set A is I mean, you cannot, all these sets are open sets, okay. So yes, since it is compact, a set A in A cannot be written as disjoint union. written as infinite union. I mean, countably infinite, whatever. Infinite disjoint union sets in, right? Because it's infinite disjoint union, okay, and all the sets are open, so there has to be a finite cover, and it's a infinite cover, so there has to be a finite cover. So that will imply the actual disjoint union is actually finite. So it's not possible to write it as an infinite disjoint union. So this implies finitely additivity. So hence, finite additivity implies countable additivity. Of mu on this algebra E. Okay. We are defining it on mu and it's on this E. So we have got a countable additive function on mu on this. There exists Carathéodory extension. There exists which we still denote it as mu. There exists a measure on the Borel sigma algebra of 2 power of the characteristic. Okay. So we have got a measure, okay, Carathéodory measure, and we have mu of a equal to phi of 1a, which is equal to integral of 1a over x with respect to d mu. Okay. So phi of f equal to integral f d mu is satisfied for, I mean, this is satisfied for each 1a, hence for the summation for simple function with sets in A, right? Now you have an algebra, and I mean, it's an easy exercise that if you have any simple function in the sigma algebra, with sets in sigma algebra, you can approximate it by simple function with coming from sets in algebra A. I mean, if you take any set in the sigma algebra, then you can approximate it by a set in algebra A. Okay, that's the extension. I mean, given epsilon, see if you have a in the sigma algebra, B of R, then there exists a B in this A such that mu of A, if you take the symmetric difference or whatever, you take it from inside, it's an open set, so maybe you can cover it above, whatever, the regularity or whatever. I mean, we have the compact metric space, the measure is automatically regular, okay, that's what. We can approximate it from inside by compact set, from the top 5 open sets, okay. And the open sets, then we can take it from the base if you want. I'm just saying that we have it. Or you can use from the algebra you can use. I mean, that also you can do, which is in the exam also. Symmetric difference of, I mean, you have the algebra and you can approximate any set in that Borel sigma algebra by this. A minus B is less than epsilon. Given epsilon, we can get a set like this. So this implies that if then, I mean, then yeah, and it's all positive function. It's all for positive function. What kind of function? Yeah, it's true for all these kind of functions, simple function. Yeah, so I mean, then any continuous function, any measurable function can be approximated by simple functions from this. Okay, so these things implies that phi of f equal to integral f d mu for all continuous functions. This is okay. Is this fine?
Yes, sir. It's fine.
So since it's true for simple functions, so from that we can get it for any continuous function. Okay. Now we want to prove for a general compact metric space. Now, if anybody has a problem, please ask me. Now, let X be general compact metric space. Okay. Then let P from X a continuous. We have a then X is a continuous image of a Cantor set. So we have a P from X there. Okay. So now let suppose P from C of X to C is positive. We have a positive linear function. Okay. We'll come to that. We'll come to that. So let us from here we define P star from C of X to C of this by. So P star is a function from C of X to C of this Banach space to this Banach space. Okay. So P star of any F, I have to prove what is it value at some P star of F should take a value in the it's a function on Cantor set. So given some element of Cantor set, I have to evaluate on the Cantor set. So that is going to be F of P. Okay. So if you have the element of Cantor set, you can evaluate in P of that, and that then you can evaluate F. Okay, is fine. And since P is continuous, this is in Cantor set. Okay, this is in C of. You take F in C of X, then P star of F is equal to F composed with P. That will be a continuous function on the Cantor set. Okay, it's just composition. Now let us check what is the norm of this. Norm of F of P, the infinity norm, which is equal to supremum of F of P of X. Okay, where X in 2n. But then P is surjective. That is equal to supremum of X in X. And you maybe Y in X. Y in X of F of Y. Because P is surjective. Okay, so that is equal to F infinity. Okay, so P star is isometric. It's fine. It's actually a homomorphism. Okay, maybe that we don't need. P star is isometric. In particular, it is 1, 1 also. Okay, it's a homomorphism. It's clear it's a homomorphism. If you have F times G, you will get F times G there. The product, you will get the product. You just write it, you will get the product. So it's a homomorphism of algebra. If you have alpha times F, then alpha can be taken out. If you have F plus G, then F plus G, you can write it as P star of F plus G is P star of F plus P star of G. So it's a homomorphism. P star is isometric homomorphism. It's clearly a homomorphism. Okay. Okay. So now we got a homomorphism. We want to use that. So what do we want to do? So we have an isometric homomorphism, which is 1, 1. Okay, which is not onto, which is 1, 1. So what do we have? We have a P from we got a P from 2n to C of X. Sorry, from 2x. See, this is always the case. Then we can get a P star from C of X to C of 2n. Okay? Which we can always get a map like this. And if that map is surjective, this map is injective. Okay, so that's what we have used. Okay, now using this P star, which is an isometric, so whenever you have isometric homomorphism, you can actually think it's a subspace of that. Okay, so we can consider C of X as subspace of this. Okay, subspace of C of P using this P star, which is called an embedding. Okay, P star is an embedding. Any isometric homomorphism is called embedding. Okay, so C of X is embedded into C of 2n. 2n. Okay. Now you define. So now we have a phi. Did I write before? Yeah. So suppose, okay, maybe I'll write here. Okay. Suppose phi from C of X to C, positive linear function. Positive linear function. Okay. Then you consider phi. I mean, we identify C of X with the image P star of C of X. Okay. Then use Horn-Banach theorem. Horn-Banach theorem says if you have a linear function on a subspace which is bounded, okay, then you can extend to the bounded linear function with the same norm. You can extend to the whole space. Okay, get phi tilde from 2n, C of 2n. Sorry. C of X is a Banach space which is sitting as a subspace in C of 2n, the Cantor space, C of the Cantor set. Okay, then we get a phi tilde to C with phi tilde norm is same as norm phi. Okay, and phi tilde acting on any P of P star of F. Okay, P star of F, which is same as phi tilde acting on F of P. Okay, this function is same as phi of F. Okay, because that's how we are defining the. That's how we are. I mean, we take a linear functional on C of X, then we consider a linear functional. I mean, just by acting on phi at phi tilde of F of V equal to phi of F, we get a linear function on the subspace, which is just the P star of C of X. Okay, inside the C of 2n, C of the Cantor set, then we extend to a phi tilde. Okay, this thing is okay. So we get a linear function on the whole space. Is fine. Okay. So further, so we have that since phi is positive, so we have now we want to use that lemma. Our first lemma says that positivity is equivalent to saying the norm is equivalent to positivity is equivalent to saying norm phi equal to phi of 1. Phi is positive is equivalent to saying norm phi equal to phi of 1. Okay, so that we want to use both the ways we want to use. Okay, now since phi is positive, phi of 1 equal to 1. So phi tilde of 1 equal to phi of 1 with phi, but then 1 acting on phi is again 1, okay, which is phi of 1. And I mean, this one is on Cantor set, this one is on the X, okay, which is equal to what? Which is equal to norm phi, and which is same as norm phi tilde, that by the Horn-Banach extension, okay. So this implies phi tilde is also positive. We have used the lemma both the ways. Phi is positive, so phi of 1 is phi of 1 is norm phi. I mean, you can take it to be 1 if you want. Okay, that doesn't matter. Phi of 1 is also phi of 1 equal to norm phi. Since let me come again. Phi is positive, so phi of 1 is equal to norm phi. Okay. Use that fact to get that phi tilde of 1, which is also same as phi of 1. So we get, which is equal to norm phi tilde. Norm phi and norm phi tilde are same. So for phi tilde also the norm is equal to phi tilde of 1. So phi tilde is also positive. Okay. So there exists a mu. Maybe we call it as nu on 2n, okay, such that phi tilde of any, here I have to use a different f, such that phi tilde of any g equal to integral g, sorry, this is d nu over s. Okay. So since we have already proved the Riesz representation theorem for Cantor set, phi tilde G equal to this. Okay. Okay. Now we want to consider what is phi of f. Phi of f. Okay. Phi of f is same as phi tilde of p star f, which is f of p. Okay. F of p. Okay. Now this is, we know that this is equal to, I mean, we can write it as p star f. That's the embedding. Now this is same as phi star of f is nothing but f of p. Okay, f of p d nu like this. Okay. This is okay. Okay. Now you define a new measure. Now, so here I will make a slight digression. Now take mu equal to, you have a map p from there. I mean, you have a map from p to 2n, right? Then you define a measure mu equal to mu p. That is mu of A equal to mu of P inverse of A. See, P is a continuous function. Okay. So if we have a in the Borel sigma algebra of X, then P inverse A is in the Borel sigma algebra of a Cantor set. Okay. Now you can define a measure mu of A equal to by this prescription. P inverse A is a measurable set, so mu of P inverse A. In fact, this is a digression. If X is a measure space, X is a measurable space, and you have a Y, some G is another. These two are measurable spaces, and mu is a measure on X this. Okay, and you have a T from X to Y, which is measurable. That is, you take the inverse image of any measurable set here, you get a measurable set here. Then you can define a new measure, mu T inverse. You can define new measure, mu T inverse of A equal to mu of T inverse A. Okay, for all A in script F. My internet is, I got a new internet, but still it says it's uninstalled. I don't know. Okay, this is fine. So then, integral of any f, if you have a function on y with respect to d mu t inverse, okay, is same as integral of f of t. F of t or integral of f. Yeah, that's right. F of t of t. Yeah. F of t is a function on x. Okay. I mean, this is true for any indicator function because the measure is defined like that. So it is true for any simple function. Okay. Then any function can be approximated by simple function. Any positive function can be approximated. It's trivial. Okay. It's an exercise. Check this is an exercise. It's true for any characteristic function or indicator function. It's true for any simple function. So then for any measurable function. I mean, any integrable measurable function. Okay. So this is the change of variable formula. This is the ordinary change of variable formula. I said for the presentation from change of variable formula, that is a different thing. Okay, that's the usual using Jacobian and other thing, which you can get it through this. Okay. Okay. So what do we have? Now we want to calculate that phi of f. We have got a measure on the Cantor set, and we have a function from the Cantor set to this our original compact set. And using that function and the measure on the Cantor set, we brought back the measure. I mean, if you have a transformation from one measure space to other measure space, then you can use, by taking the inverse image of set, you can bring back the measure to this set. Okay, so that's what we have done. I mean, by taking the inverse image and defining this using this measure, you can get a measure on the image space. Okay. Now phi of f Okay, now phi of f equal to phi tilde of, so I have written all that. So I have written phi of f equal to, I have written here. So which is equal to f of p, maybe I will write it again. Phi tilde of p star f, which is equal to integral of f of p d nu over this. Okay. But then by change of variable integral over x, yeah, f d nu, where mu equal to mu px. So we have got a measure on this. Okay, notice that not just here, I have missed somewhere that there is a uniqueness in this. See, we have got a measure on an algebra and then we extended that, okay, for the Cantor set. So maybe I will write. So Riesz representation, where is it? Yeah. Then there is this, where did I state the theorem? Oh, didn't I state the theorem? Okay. I didn't state the theorem. Is that you didn't ask me? Statement of the theorem. I mean, I said it orally, but I didn't really state it. Okay. Phi from C of x to C is a positive linear function. Okay. Then there exists a mu on Borel sigma algebra. There exists a unique mu on Borel sigma algebra such that phi of f equal to integral f du over x. Okay, that's the statement. Okay. We first proved this statement for the Cantor set. Okay. Then we have proved this statement for a general set also by using the surjectivity of the map from Cantor set to this compact set. And this measure is unique. On the Cantor set, this measure is unique because we got a measure which is determined by this. Yeah, you are asking something.
Sir,
Yeah.
sir, like, so according to what you have written, so like the phi is from x to c.
Hmm.
But like again, you are saying positive functions. So I am confused.
X to C.
You have written that
What I have written?
in the statement of the
Oh, I will come.
theorem. You just wrote.
What I have written? X to C. What?
Sir,
Statement of the theorem is phi is from C of x to C is a positive linear function. Then there exists a unique measure mu on Bx, Borel sigma algebra, just phi of x equal to integral f dv. Every positive linear functional is given by integration. Where, what do you want? What is your
okay. Sir, like I was wondering whether it should be Cx to R.
No, it's a linear functional. It's a complex. Why it should be R? Why do you think so? Positive means it takes positive functions to positive numbers. It does not take every function to complex number. I mean, real numbers. It takes positive function. Okay, that is the positivity. Positive means f greater than 0 implies phi of f greater than 0. You can multiply by a complex number, yes, then it will be a complex number, for example. Okay, it does not take every function. It takes positive function, strictly positive function. Not strictly means not that way. It takes, I mean, it does not take any other real number. It's a positive function. Function taking positive values, it takes to positive number. That's all. Okay, it's clear?
Yes, sir.
Okay. So I have proved that.
Just wondering. Sir, also, sir, like I'm just wondering whether like this statement would hold if we like consider like Cx to be like all the space of all real functions.
Cx to be what? I
Like
didn't hear the
instead of
last.
Cx, like we consider the
No, either an internet problem or something.
I am
Either instead of Cx, you want to consider what?
the space of all real functions.
Space of all real function, real valued function instead of C. I mean, what is that you are going to achieve? You will have a real valued function. That's okay. So then any real valued function can be written as, no, what is the statement? Phi is a, you want to take Cx taking values in R. Is that what you want to say?
Yes, sir.
Huh?
Yes. Yes, sir. Like I'm just wondering whether
R is,
like the statement would
I mean, see, if you have take Cx of R, then I think it should be true. I have never, I mean, we don't consider non-complex, I mean, real Hilbert spaces. But Cx really is something which is, I mean, it's actually, you can embed into Cx, I mean, Cx with complex valued function. I'm sure it will work for our real valued one also. I don't see any big difference. I mean, you can get that from this statement, I believe. Okay.
thank you, sir.
Okay. So the uniqueness we want to consider. The uniqueness is when we were dealing with first we were dealing with Cantor set. The Cantor set we defined the measure like this. Okay, mu of A equal to phi of 1a, and this has to satisfy because it satisfies the integral condition. I mean, so if a measure satisfies the integral condition, the measure is it has to satisfy this condition for all a in that script a. Okay, it satisfies that. But then a measure on an algebra, the extension is unique. Okay? The measure is actually determined by its value on the algebra. Right? So because of that, the extension is unique. There does not two extension. Okay? Because the characteristic extension is unique. Because of that, you get a unique measure on the Cantor set. Okay. Now we want to prove this. So when we consider Cantor set, it's unique. Now we want to prove the uniqueness for a general set here. Okay. Okay. To complete proof of theorem. I mean, I am stated the statement. I mean, this is the statement of the theorem, which I forgot to state initially, but which I said orally. After writing the lemma, proving lemma, I thought I initially wrote the statement of the theorem. I continued with that. Okay. Okay. So now to complete the proof of the theorem, we need to prove uniqueness. Need to prove uniqueness of. So why is mu unique? So we want to say that mu is actually determined by the phi. I mean, given a phi, there is a unique mu. That's what we want to say. So we want to say that somehow that mu is determined by phi. Okay. So for that, we make the following claim. Mu of k for any compact set. I mean, it's any closed set is compact here because it's a compact metric space. For k contained in X, mu of k equal to, we get infimum of integral over, there is no integral. I want to make this phi of f, where f is less than, f is greater than or equal to this indicator function on k. Okay. So this mu is whatever, we have a phi. What I mean to say is we want to prove the following. Maybe I will write it more clearly. We want to prove the uniqueness of this mu. Okay. Suppose we may get two measures or something which satisfies that. Suppose mu some arbitrary measure which satisfies mu satisfies phi of f integral equal to integral f d. Okay, where phi is a positive linear functional and this. Okay, then mu of any set k contained in X closed, okay, a closed set, equal to infimum of, I want to write a bracket by go to integral, infimum of phi of f, okay, and this f is greater than or equal to indicator function k. Okay, this is the claim. Oops. Okay, so why is this true? Okay, so first thing is, if 1k is less than or equal to f, okay, as functions, then integral 1k d mu is less than or equal to integral f d mu, and this is equal to phi of f, okay, and this is equal to mu of k. So mu of k is less than this. So this implies mu of k is less than or equal to phi of f for all f greater than 1k. Okay, so we have proved the one way of the inequality. Okay, now we want to prove that the infimum is actually attained. That's what we want to prove. I mean, we want to prove that this is actually infimum of over all such f. That's what we want to prove. Okay. Okay. K is compact, contained in X is compact. Okay. So there exists UN open such that intersection of UN equal to K. I mean, K is a G delta set. G delta, whatever it's called, G delta. That is just clear, no? I mean, you might have studied Urisan lemma. See, K is compact, then you have this function. You consider all those x in X, that dxk is greater than 1. Call this as way. Okay, then intersection of UN. You know this function. I assume you have gone through these things. Is this a problem to anyone? I take this function. You have the metric. It's a metric space. X is a metric space. So you take dxk greater than 1, all such x. That's an open set, of course. This function is a continuous function. Okay, this is an open set. Then you consider this set. This is UN. I mean, this we went through in analysis course. When you want to prove the Urisan lemma, we use this. Okay, this is fine. In fact, choose. I mean, define. Fn of x equal to dxk divided by dxk plus dxun complement. You define it like this, then Fn is greater than 1k and less than or equal to 1. Fn takes the value 0 in k and 1 in un complement, and this is a function like this. No, it's not less than or equal to 1. Yeah, it's less than or equal to 1. It's less than or equal to 1. In fact, 1 un. 1 un. 1 un or 1 un. It takes the value 0 there. Sorry, it takes the value 0 there, which is less than or equal to 1 un. Okay. Is this fine? This is something I don't know. In my course, we go through this or I will ask someone to do that. This is the Urizan lemma. When you have two closed set, okay, then you have a function which takes the value 0 in one set. You have a continuous function. Two disjoint closed set. Then you have a function which takes the value 0 in one of the closed set and 1 in the other set. And that is precisely this function. Where this function dxk, this is a uniformly continuous function. If you have any closed set, then you can define a distance between the closed set and a point. So if anybody don't know this, you just tell me. I will go through the whole thing in full detail. Or I will give you an exercise. Is this fine? Okay, someone say fine. I will just continue. If it's not fine, someone.
It is fine.
I'm sure it's fine for some people. I mean, especially those who I have done it in my analysis course. So I just want to know whether it's not fine with anybody. If it's not fine, you please tell me. Okay. So you have a Fn which is greater than this, and we know that it looks like this. And since Un decreases to k, Fn goes to Fn decreases to 1k. So okay, then this implies phi of f, whatever we have there. Here I have written something nonsense. This is not integral. I'm sorry, this is not, that's okay. But mu of k is less than, this implies phi of 1k is less than or equal to phi of f. That's what I want to say. Okay, from that, okay. Then phi of f decreases to phi of, which is equal. Or you can take the integral that is defined by the integral. That's also okay. So whatever our claim is proved, our claim is 1 mu of k equal to this. Okay. But now on a compact metric space, the measure is determined by its value on the closed subset because it's inner regular. Since any measure on compact metric space is inner regular, that is inner regular means you can approximate the measure by compacts from inside. So it is in fact the measure is determined by its values on the compact side. That is mu is determined by values on compact sides. Okay. So this implies mu is unique. Mu is uniquely determined by phi. Okay. So we have the uniqueness for the Riesz representation theorem. So I think the whole thing is proved. And we got a regular measure on this. So the Riesz representation theorem is proved. So if you have any doubt anywhere, you ask me. If you want me to go through any argument, you ask me. Okay. What we did is the following. If we have a positive linear functional on a positive linear functional on C of x, where x is compact metric space, then that linear functional is actually given by integration with respect to some measure, positive finite measure. It's a finite measure, of course. Okay. The measure is defined on the counter set, which is finite measure, which is defined on this. By its definition, it's how we proved this. First, we proved it for counter set by taking from finite projection and all those things on those base set. Then, if we have anything on the x, then we took the surjection from any counter set, and we had a homomorphism, injective homomorphism from C of x to inside into that C of the counter set. Then we extended that linear functional to the whole of that. Okay. Then we get a measure on the counter set. Then using this surjection, we brought back that measure to this x. And that is the measure. Okay. That measure satisfies the required condition. On the other hand, it is unique because of whatever this is determined on the compact set, which we have. Okay. So that's all. If you have any question, you ask. It's fine. Okay, I will end it. We will meet tomorrow. Tomorrow, Chaitanya is talking on Fourier series. Those who know Fourier, I mean, you can attend anyway. Okay. You have, yeah. So once again, I will stop recording. If you want to ask something else, then I will stop recording. Apart from whatever, you want to ask something else?
No, I was just asking. Time is usual time, right?
Is usual time, 5 o'clock. Okay. Okay, I will end the session. Bye.